Welcome to Factory on Air by DBR77, where smart manufacturing gets real. This is episode 8, OEE under the microscope, how to spot and eliminate losses. Knowing your OEE isn't enough, what matters is what you do with it. In this episode, we break down the real causes of poor equipment effectiveness and how to fight back using IoT data, downtime analytics, and digital twin simulations. You'll learn how to detect micro downtime, reduce changeover losses, and visualize bottlenecks like never before. We'll also share how DBR77 helped one manufacturer raise their OEE from 62% to 75% in just 6 months, and cut defects by 12%. Factory on Air is powered by DBR77, the all-in-one platform for production intelligence, predictive analysis, and continuous improvement. Let's dive in.
Welcome back to The Deep Dive, the show where we unpack complex topics and hopefully turn them into actionable insights for you.
Great to be here.
Have you ever walked into a bustling factory, or even just thought about your own busy day, and wondered why some processes just hum with efficiency?
Yeah, you see it, don't you?
While others seem to struggle with, unexpected downtime, wasted resources, or just, a general sense of sluggishness.
Absolutely. Or maybe you're just curious about how cutting-edge technology is fundamentally changing traditional industries, making them smarter, faster.
More responsive, yeah.
That's a feeling many can relate to, I think, whether it's a massive production line or just like a personal project you're trying to manage.
Exactly. So today we're taking a deep dive into a really powerful metric, one that's, often overlooked or maybe understood only superficially.
That's right. We're talking about overall equipment effectiveness, or OEE.
OEE.
And it's so much more than just a simple number, Think of it more like a sophisticated diagnostic tool, a window into the true health of any operational process.
And any process.
Yeah, basically. It's designed to reveal not just the obvious surface-level issues, but also those hidden losses and the massive opportunities for significant, measurable improvement that might otherwise go completely unnoticed.
Hidden losses. I like that. And for this deep dive, we've gathered, quite a stack of sources.
We have
a detailed exploration of OEE itself, breaking down its components, shining a light on common pitfalls, and outlining some practical strategies for boosting it.
Mm-hmm.
Then we're also pulling from a comprehensive overview of a pioneering digital transformation platform. It's called DBR77.
That's right, DBR77.
And this platform directly addresses many of the challenges we'll discuss today, particularly through its innovative applications of IoT, digital twins, and advanced AI.
Yeah, it ties in perfectly.
So our mission today is really to go beyond just defining OEE.
Absolutely. Our goal is to show you not only what OEE is and why it's absolutely critical, but also precisely how you can pinpoint
Good point, yeah.
and then systematically eliminate losses, even those tiny elusive ones that feel, impossible to track sometimes.
Those sound like the worst ones.
They can be. We'll explore how modern technology, brilliantly exemplified by the DBR77 platform, provides the exact tools and the deep insights necessary to achieve real, measurable gains in both efficiency and quality.
Okay.
This deep dive should offer some genuine aha moments, I hope. Things that could fundamentally change how you think about operational excellence, no matter what your field or industry is.
All right. Sounds good. Let's start by demystifying this foundational metric then. Okay, let's unpack this. So, at its core, what is OEE? We hear this acronym thrown around a lot, especially in manufacturing, but it's clearly more than just a quick calculation, isn't it?
Oh, much more than just a calculation. OEE, overall equipment effectiveness, it's a comprehensive metric. It's designed to evaluate the total effectiveness of a piece of equipment or even an entire production line.
Total effectiveness, okay.
It's truly a holistic view. It combines 3 critical components that together measure how well an asset is performing against its theoretical maximum potential.
Its absolute best.
Exactly. You can think of it as the ultimate scorecard for your machines, basically.
And those 3 core components are availability, performance, and quality. Let's break those down. First up, availability. What does that truly encompass?
Okay, availability. It's essentially the ratio of the actual time a machine operates compared to the planned production time.
So run time versus planned time.
Right. Think of it as, is the machine ready to run when we need it, and for how long was it actually running? What impacts this component are all the events that cause the machine to stop when it should be running.
So not just breakdowns.
Not just breakdowns, though. Those are obviously a big part. The obvious machine failures, they're easy to spot. but availability also encompasses less obvious factors, like material shortages.
Waiting for parts.
Exactly. If the machine is just sitting there waiting for raw materials because, say, the upstream process is delayed or the warehouse didn't deliver on time, well, it's not available to produce, is it?
Makes sense.
And crucially, it also accounts for long changeover and setup times between different products or tasks.
Booting jobs.
Yep. So if your planned production time for a shift is, say, 8 hours, but 2 of those hours are spent on a complex changeover.
2 hours. Wow.
Oh, yeah, sometimes more.
Oh.
And maybe another hour is lost just waiting for components to arrive at the line. Well, then your machine was only truly available for 5 hours, not 8.
So that hits your availability score hard.
Significantly. It's all about being prepared to work when planned.
So it's not just about the machine being broken, but anything that prevents it from being available to make products.
Yeah.
That makes perfect sense. Now, what about performance? That sounds like it's about speed.
They're on the right track. Performance is the ratio of the actual output to the theoretical maximum output during the time the machine is operating.
Okay, so when it is running, how fast is it going?
Precisely. This isn't just about the machine running, it's about it running at its optimal designed speed. If your machine is supposed to produce, say, 100 units per hour,
Yeah.
but it's consistently only producing 80, well, your performance is suffering. It's only 80% performing.
What causes that slowdown?
What degrades performance? Things like slow production cycles. Maybe the machine operates below its standard or theoretical speed due to wear and tear or suboptimal settings that were never quite tuned right.
Or even slightly off materials.
Or even slight variations in raw material quality. Absolutely. It also includes those minor stoppages or brief hesitations. We're talking literally just a few seconds or maybe a minute.
Little hiccups.
Exactly. Those little hiccups that might not be considered full breakdowns, but they still slow down the overall flow. These small, often overlooked moments can cumulatively reduce your output significantly.
So you're losing capacity even when the machine is technically on.
You got it. You're effectively losing potential production time.
Okay, so even if the machine is available and running, if it's running too slow, your OEE takes a hit. And then finally, quality. That must be about the output being correct, right? Meeting spec.
Precisely. Quality, in the context of OEE, is the ratio of good products produced to the total products produced.
Good parts versus total parts. Simple enough.
Simple concept, huge impact. This is about ensuring that what you do produce is actually usable and meets specifications, even if a machine is available and running fast.
Right.
Like really fast.
Yeah.
If it's producing defects, rejects, or products that need costly rework, its overall effectiveness is severely compromised.
Because you wasted time and materials.
Exactly. Every defective product represents wasted material, wasted energy, wasted time. Imagine you're running at full speed, but 15% of your output goes straight to the scrap bin.
Wow.
Your machine was available and performing, but a significant portion of its output isn't contributing value. This directly reduces your OEE score and, importantly, hits your bottom line hard.
So availability, performance, and quality. They aren't just separate metrics you add up. They're truly multipliers, aren't they?
Right.
If any one of them is low, your total OEE plummets dramatically.
It absolutely does. OEE, availability X, performance X, quality. If any one of those factors is 0, your OEE is 0. If any are low, the whole thing drops fast.
Wow.
That's why OEE isn't just a simple calculation that gives you a single number. It's such a powerful diagnostic tool. A low score in any one of these 3 areas immediately points to a specific type of loss.
It tells you where to look.
Exactly. For instance, if your overall OEE is low primarily due to poor availability, to investigate downtime causes breakdowns, material delays, those long changeovers.
Yeah.
If performance is the primary issue, you look at cycle times and those minor stoppages, the hiccups.
Got it.
And if quality is low, you focus on defect rates, scrap, rework processes. It directs your efforts exactly where they're most needed, preventing you from chasing the wrong problem.
Okay, so we understand what OEE is at its core. But why is it crucial? You said it applies beyond the factory floor. How does this really impact a business or even, dare I say it, our daily lives? I'm thinking about my own workflow right now.
Well, beyond the factory floor, OEE is strategically vital for management. Think about it. A high OEE means machines are operating efficiently, producing high-quality products, and experiencing minimal downtime.
Which
Translates directly into significant cost savings, increased throughput, higher profitability, and better customer satisfaction due to consistent product availability. Happy customers.
can't argue with that. And for management.
For management, knowing their OEE enables much better production planning. You can actually accurately forecast how much you can truly produce, not just guess.
Right. Realistic planning.
It informs critical investment decisions in new machinery or upgrades. It tells you exactly which assets need attention or replacement based on data, not just gut feel.
Okay.
And it allows for optimized resource allocation, ensuring that capital, labor, materials are used as effectively as possible across the entire operation. Less waste, more value.
And you mentioned it's universally applicable. I'm thinking about my own workflow again. I definitely feel like I have an OEE for my podcast prep. It's not always great.
You absolutely do. Even if you're not managing a multi-million-dollar production line, the core principles of OEE, maximizing the availability, performance, and quality of any asset or process, they're universally applicable.
So my personal OEE.
Exactly. Think about it. Are you always available for the tasks you need to accomplish? Or are you constantly interrupted by notifications, maybe held up waiting for information, or sidetracked by unexpected meetings? That's availability loss.
Uh-oh, guilty.
And are you performing at your peak efficiency when you are working? Or are there slow cycles because you're multitasking maybe? Or those minor stoppages where you briefly lose focus and, scroll social media for a minute?
Okay, stop reading my mind. That's performance loss.
And is the quality of your output consistently high? Or do you find yourself needing to rework things frequently because of distractions or maybe rushing? That's quality loss.
This is hitting close to home.
It's a really valuable lens for self-assessment and continuous improvement in almost any context. It helps you identify your own hidden losses and become more effective wherever you work.
That's such a relatable way to think about it. My personal OEE needs work. Now, let's dig into why OEE often falls short in, say, a manufacturing setting. It's not always about the dramatic, obvious...
Exactly. But the truly problematic issues are often less dramatic and much harder to spot. Let's start with what we call frequent unplanned machine downtimes. These are direct hits to availability.
Unplanned stops.
Yes. They include catastrophic equipment failures, a grinding halt, smoke, alarms blaring, the whole 9 yards. But they also encompass crucial factors like, as we mentioned, material shortages.
Waiting again.
Right. If a machine has to sit idle for half an hour because the right components haven't arrived at the line or maybe the forklift operator is delayed, that's unplanned downtime just as much as a mechanical fault.
Even if the machine is fine.
Exactly. The machine is perfectly capable, but it can't do anything useful. It's not available.
So it's not just about the machine itself, but the entire supply chain and logistics impacting its ability to run. Okay. What about the time it takes to get things ready? I'm thinking of how long it takes me to switch between complex tasks sometimes. Feels like wasted time.
That leads us perfectly to long changeover and setup times. These are the periods required to switch a machine or a production line from making one product to making another, or even just preparing for the next batch of the same product.
Like changing tools or settings.
Exactly. Imagine a printing press switching from one book cover design to another. The time spent cleaning, swapping plates, reconfiguring the machine, setting new parameters for the new product. It significantly reduces availability.
Especially if you make lots of different things.
Especially in environments with varied production, think customized goods or just a wide product portfolio, these setup times can eat up hours, sometimes even days of potential production time.
Wait, that is.
Oh, absolutely, in some industries. Yet they are often seen as a necessary evil, sort of an unavoidable cost of doing business rather than a prime target for reduction.
So they get accepted even if they're inefficient.
They often become part of the planned downtime, but the reality is they're frequently far longer than they truly need to be if optimized.
And once it's running, it still might not be running as fast as it should. That seems like a common frustration I hear about. It's running, but it's slow.
Exactly. That's slow production cycles. This refers to machines operating below their standard or theoretical speed, even when they're technically running and available.
Just
sluggish. Sluggish is a good word. Perhaps it's a worn-out component causing friction, maybe a suboptimal setting that was never fully tuned after the last maintenance, or even, like we said, less than perfect operator input causing slight hesitations.
So multiple possible causes.
Many. Whatever the reason, if your machine is designed to produce 100 units per minute but is consistently churning out only 90, well, you're losing 10% of your potential output right there.
That adds up fast.
It directly impacts your performance component. You're simply producing less than you could in the available time without a full stop. It's often ignored because, hey, the machine is running, just not optimally.
Right, at least it's working.
That kind of thinking, yeah.
And then, even if it runs fast, if what it produces isn't good, that's got to be a major headache. Scrap and rework.
Then you have production defects and rejects. This is where the quality component of OEE takes a significant hit. If a machine produces items that don't meet specifications.
Bad parts.
Right. Whether they're completely unusable rejects that go straight to scrap, or maybe they require costly rework to bring them up to standard, that represents wasted materials, wasted energy, wasted time, and ultimately lost revenue.
It hits everywhere.
The machine was technically available and maybe even performing at speed, but its output isn't contributing value. Addressing these issues often requires looking really closely at precise process control, machine calibration, raw material consistency, operator training.
A whole range of factors.
It's about not just making something, but making the right thing the first time.
This all makes sense, these big categories. But you mentioned one sneaky culprit earlier that I'm really curious about. Micro-stops. You said this is where it gets really interesting. What makes them so insidious?
Micro-stops, yes. These are the absolute bane of true operational efficiency because they are so subtle, so brief, and often completely undocumented.
Undocumented. How brief are we talking?
We're talking about stoppages that last just a few seconds, maybe up to a minute, maybe two. Think of a brief jam that an operator quickly clears by hand.
Oh yeah, like a little snag.
Or a sensor glitch that quickly self-resets, a momentary hiccup in material flow that causes a brief pause, or even just an operator having to briefly reach in and adjust something on the line.
Things that happen all the time.
Exactly. Individually, they seem insignificant. Oh, it only stopped for 15 seconds. I fix it immediately. No big deal.
Right, didn't even log it.
Precisely. But cumulatively, they create significant losses that often go completely unnoticed or are simply ignored because they're too small to track manually or not worth logging.
Death by 1,000 cuts, you called it.
It's the perfect analogy. They erode performance and availability slowly, almost invisibly, but their cumulative impact can be enormous, easily far outweighing a single major breakdown over the course of a year.
Wow.
Many companies, honestly, could probably recover hours of production per day just by finding and addressing these tiny, frequent interruptions.
That's a powerful analogy.
Right.
And I imagine these causes aren't isolated, are they? They're probably interconnected. A microstop could even be a warning sign for something bigger.
Absolutely. That's the in-depth analysis aspect we need to consider. They're often linked. For example, poor setup procedures resulting from long changeover times can directly lead to quality issues later on if the machine isn't perfectly calibrated for the new product run. Or a machine running at slow production cycles due to, say, a worn part might start experiencing more frequent microstops that part degrades further.
So one problem leads to another.
And you're absolutely right. Microstops can often be precursors to larger breakdowns. A machine that's frequently hiccuping or briefly jamming might be signaling a deeper mechanical problem that will eventually lead to a full, unplanned, and much more costly stop.
So catching them early is key.
The fundamental challenge is often identifying these issues, especially the subtle ones like microstops. If you don't even know they're happening consistently or why, you can't possibly fix them. You need the data.
That's a great point. And thinking about my personal OEE again, I could definitely relate to those micro-stops in my own day, the brief distractions from email pop-ups that pull me off task, the inefficient switching between applications that just breaks my focus, or the moments waiting for a slow computer or that vital email response. These accumulate and absolutely erode my personal OEE.
They really do.
It makes me wonder how many hours I actually lose to these personal micro-stops each week. Probably more than I want to admit.
Precisely. The principles are universal. Those brief moments of context switching, the minute or two spent searching for a file, or the quick mental break that accidentally turns into 5 minutes of scrolling, they all chip away at your focus and productivity, just like a machine's effectiveness is eroded by those constant tiny interruptions.
Identifying and minimizing them is key. Okay, So the challenge isn't just knowing what OEE is, but actually seeing those hidden losses, especially the microstops. This means we absolutely need to move beyond manual logs, right? Because they can't possibly capture all those brief, sneaky interruptions. A human simply isn't going to log every single 15-second pause.
You're exactly right. Traditional manual logs are inherently limited. They're prone to human error, simple forgetfulness, or just a lack of time on a busy production floor.
Makes sense.
To truly shine a light on these losses, especially the microstops, we need the power of IoT sensors. Installing dedicated Internet of Things sensors directly on machines and across production lines allows for incredibly precise, real-time data collection.
Real-time data, what kind?
Yeah. Well, these sensors aren't just logging if a machine is simply on or off. They register crucial parameters like machine runtime, idle time, specific operational data like temperature, pressure, vibration, energy consumption.
Wow, really detailed.
And even the number of cycles completed, often down to the millisecond. This granularity of data is what makes the invisible visible. It captures every single nuanced operational state, every little pause.
So it's not just about when a machine stops, but crucially, getting the data to figure out why. That seems like the real investigative part. You need the context.
Absolutely. That's the critical element of capturing the why. It's vital to identify the causes of stoppages, not just the duration. Now, some of this can still be done through manual declarations by operators. Maybe they select a reason from a drop-down menu on a terminal.
Which might be inaccurate.
Exactly. It can be prone to human error, oversight, or just picking the easiest or most generic category like other. The more accurate and efficient way is often through automated classification systems.
Automated.
Using AI, often. Machine learning algorithms can interpret patterns in the sensor data leading up to a stop and automatically classify the likely reason. The goal isn't just to know when a stop occurred, but why it happened. Was it a material jam detected by a specific sensor? A tool change indicated by a pressure drop? A quality issue flagged by a vision system? Or something else entirely?
That distinction is crucial.
It's fundamental for effective problem solving. Otherwise, like we said, you're just reacting to symptoms without knowing the disease.
And this continuous, precise data collection for those tiny, fleeting moments, those microstops, that sounds like it's building something really significant over time. Almost like a detailed historical record of every single stutter the machine makes.
It is. It's about building a database of the invisible, especially for those microstops. This is absolutely critical for aggregating what seem like small, frequent interruptions into a significant, analyzable data set.
Seeing the cumulative impact.
Precisely. Individually, 15 seconds might seem negligible, almost not worth bothering about. But if that same 15-second stop happens 50 times a shift, across multiple machines on a line, that quickly adds up to hours, even days of lost production over a month or a year.
That's huge.
A dedicated database makes these cumulative losses quantifiable and therefore targetable. I remember one company, they implemented this kind of tracking and realized their operators were collectively losing nearly an hour and a half per shift, just clearing small jams that lasted less than 30 seconds each.
An hour and a half per shift.
Thousands of hours a year that were completely invisible before they started tracking automatically.
So once you have all this data pouring in, you can start analyzing it in real time, which means you can react much faster, perhaps even proactively. You're not waiting for a weekly report to discover you had a bad day 3 days ago.
Exactly. That's the real power of real-time analysis for rapid intervention. When data is flowing in continuously, you can quickly detect trends that indicate developing problems or recurring losses as they happen.
Like seeing a warning light.
Kind of. Imagine seeing a specific machine's performance starting to dip slightly over a few hours, or the frequency of a particular type of microstop slowly creeping up. This allows for proactive rather than purely reactive responses.
So you can step in before it breaks.
Instead of waiting for a machine to completely break down, you can see a problematic pattern emerging and intervene before a major issue arises. Maybe you schedule preventative maintenance during the next planned stop, or adjust a parameter slightly.
Okay.
This capability shifts operations from constant crisis management to planned preventative action, which saves significant time, money, and stress.
And just collecting mountains of data isn't enough. You need to organize it somehow, right?
Yeah.
That's where categorization comes in, I assume, to make sense of the potential chaos.
Yes. Absolutely. Categorization for targeted action is essential. You need to classify downtimes in a meaningful, granular categories, not just downtime, but things like technical failures may be broken down further into electrical, mechanical, pneumatic material shortages, operational errors, scheduled maintenance, quality issues, changeovers, and so on. This level of categorization is crucial because it enables far more accurate and effective corrective actions.
How so?
Well, if you just know machine XYZ stopped for 2 hours due to malfunction, that's not very helpful, is it?
Not really, no.
But if you know machine XYZ stopped for 2 hours due to hydraulic pump failure on the main press axis, now you can dispatch the right technician with the right parts, and you can investigate why that specific pump failed. Was it overdue for service? Was there contamination?
It lets you address the root cause.
Exactly. You get to the root cause, not just the symptom.
This is clearly where DBR77 really steps in, isn't it? Their IoT solutions sound like they directly address these challenges, making sure you have the right data, the context, the classification.
Precisely. This is where DBR77's advanced IoT solutions truly shine. They provide the dedicated sensors, the connectivity, and the sophisticated data management systems necessary for precise, real-time operational data collection from employees and production lines.
So they handle the whole data pipeline.
Pretty much. DBR77's big data and industrial IoT solutions are designed from the ground up to ensure data accuracy, significantly reduce the time needed for analysis, and lower the overall information acquisition costs for their client.
Which makes it more accessible.
Right. This directly supports better operational management and enables faster, more accurate decision-making. And importantly, it specifically counters that common problem of data dependency for advanced AI and digital twins.
How so?
Because DBR77 provides the hardware and data collection support needed to ensure that the data fed into those complex analytical systems is high quality, complete, timely, and readily available. They're not just providing software, they're providing the essential foundational data infrastructure that all advanced analytics absolutely rely on. You can't build insights on shaky data foundations.
That real-time data collection through IoT is clearly a game changer. Getting that granular data, understanding the why, it's huge.
Yeah.
But what happens with all that data? Where does it go? This brings us to another really cutting-edge technology that DBR77 leverages heavily. Digital twins. What exactly is a digital twin in this industrial context, and how does it relate back to improving OEE?
Right, the digital twin, it's a fascinating concept. DBR77's digital twin technology involves creating a virtual and mathematical model of a real physical production plant or a logistics center.
A virtual model, like a 3D picture.
More than just a picture. Imagine it as a living, breathing digital replica, a perfect mirror image of your physical operations. It's not just a static 3D drawing or a blueprint, it's an active, dynamic model.
Dynamic how?
Crucially, this 3D model is integrated with that real-time data streaming in directly from those IoT systems we just discussed.
So it's connected to the real world.
Exactly. This means it accurately mirrors every production line, every individual machine, even the flow of materials, inventory levels, maybe even personnel movements in the real physical plant. And it's constantly updating in real time based on the sensor data.
So it reflects what's actually happening right now.
Precisely. It's a precise, dynamic digital counterpart that reflects the current state and behavior of its physical twin.
So it's not just a copy, it's a connected copy that understands the dynamics.
Yeah.
Okay, that's cool. But how does that help unlock predictive power for improving OEE? It sounds like you could maybe play out scenarios.
That's exactly where it becomes transformative. It allows for incredibly powerful scenario modeling. The digital twin lets you virtually rearrange factory layouts. You could adjust machine settings, change operational parameters like conveyor belt speeds, or even simulate different workforce allocations, all within this risk-free virtual environment.
Without touching the real factory.
Without touching the real factory. You can ask complex what-if questions without ever disrupting your live operations. This is where the predictive power truly comes into play for optimizing OEE.
And the key benefit here must be the ability to simulate the precise impact of proposed changes on OEE before you actually implement them in the real world. That sounds like a massive risk and cost reduction. You don't have to shut down a line for a week and just hope for the best.
It is a monumental benefit, absolutely. This ability dramatically reduces the risk and the cost associated with trial and error in a live production environment. Think about it. Instead of shutting down a line for days, maybe spending significant capital on reconfigurations and potentially suffering massive losses if the change doesn't work out as planned,
Yeah, that sounds stressful.
you can run countless simulations in the digital twin. You get immediate, accurate feedback on how a proposed change will likely affect availability, performance, and quality before committing any real resources, time, or capital.
So you optimize it virtually first.
It allows for optimization in a low-risk virtual sandbox. This accelerates innovation and significantly de-risks major operational decisions.
I could see how that would help with big changes like a new layout. But what about those tiny, elusive problems we keep talking about, like bottlenecks and those micro-stops? Can the digital twin help find those too?
Absolutely. The digital twin excels at visualizing and pinpointing bottlenecks and those elusive microstops within the virtual environment. Because it's a complete and real-time mirror of the physical world, it can highlight problem areas that might be incredibly hard to observe or trace consistently in the fast-paced, complex physical factory environment.
So it makes the invisible visible again.
In a way, yes, it uses sophisticated techniques like stochastic scenario analyses for this.
Stochastic? What's that?
It basically means it can model scenarios that include a lot of inherent variability and randomness, things like fluctuating customer demand, unexpected delays in material deliveries, or even the probability of minor equipment glitches happening.
So it's more realistic than a simple model.
Much more realistic. This gives you a much better picture of how changes will likely impact complex dynamic systems, making it easier to diagnose problems that might be hidden in the averages or hard to see in the physical world. Through these simulations, you gain incredible predictive capabilities.
Like what?
You can predict the likely outcomes of organizational changes, new machine settings, different maintenance schedules, or process modifications, enabling precise optimization before any real-world disruption occurs.
This sounds incredibly advanced. And I read that DBR77 takes it even further by integrating VR and AR, virtual and augmented reality. How does that work? How does that enhance the digital twin experience?
Yeah, that's the next level of immersion and practical understanding. DBR77 integrates VR and AR technologies with the digital twin.
So you can step inside the model.
Exactly. This means managers, engineers, even operators aren't just looking at a 2D or 3D model on a screen. They can literally step into the simulated environment using a VR headset, experiencing the proposed new factory layout or process flow as if they were physically standing there. Or with AR, they can use tablets or smart glasses to overlay digital information and simulations onto the real physical equipment or workspace.
What's the benefit of that immersion?
It allows them to experience proposed solutions and evaluate planned changes in an incredibly realistic, intuitive, and immersive environment. It helps them better understand the spatial implications, the material flow, the ergonomics for workers, and the overall impact of a change. It minimizes the risk of errors or unforeseen consequences and really increases buy-in from the team before any actual deployment takes place.
So you could walk through your redesigned factory floor before a single wall is moved or machine bolted down.
Precisely. Imagine test driving a new factory layout or a completely new process flow in a virtual world before committing potentially millions in real resources. It sounds futuristic, but it's happening now.
It sounds like it reduces risk, speeds up innovation, and really ensures that changes are truly optimized for maximum OEE and efficiency. It's a huge leap from relying on static blueprints or complex spreadsheets. It feels like living the future of operations management. So with all this incredible data flowing in from IoT and the predictive power of digital twins, it's not just about identifying problems, it's about translating that information into actual measurable gains. Can you give us some concrete examples of what these insights can achieve relatively quickly? In terms of quick wins maybe, but also big impacts on OEE. What kind of improvements are companies actually seeing right away?
Absolutely. And this is where the rubber meets the road, right? This isn't just theoretical potential. These are tangible, measurable benefits that companies are realizing by systematically applying OEE principles and leveraging supporting technologies like DBR77. One really significant area we see quick wins in is reducing changeover times.
Those setup times we talked about.
Exactly. By analyzing precise, second-by-second data captured by IoT during a changeover and maybe simulating variations in the digital twin, Companies can identify all the little inefficiencies in their setup procedures. Perhaps an operator walks too far to grab a specific tool every time, or a certain sequence of steps always causes a small delay, or two tasks could be done in parallel but aren't.
Finding wasted motion and time.
Precisely. This often leads to standardizing tools and procedures, maybe having parts or tools pre-kitted and ready at the machine before the changeover starts, or implementing parallel setup tasks where possible. We've seen this lead to a significant increase in availability, typically in the range of 5–10%, sometimes even more.
5 to 10% more uptime just from faster changeovers. That's huge.
It's immediate production time recovered without buying any new equipment. Pure efficiency gain.
That's a huge boost just for making those switches more efficient.
Okay, what about those insidious micro-stops we talked about? Can you actually reduce those significantly? They seem so hard to pin down and eliminate. Yes, and this is often where the biggest aha moments happen for companies. With improved data collection and analysis, particularly with tools like digital twins that make microstops truly visible by capturing every single second of downtime in its context.
Yeah.
Companies can achieve faster microstop detection and significant reduction. By understanding the patterns and the specific root causes of these brief interruptions, is it always the same faulty sensor acting up? Is it a slightly misaligned component causing a jam under certain conditions? Is it inconsistent material quality causing feed issues?
So you find the pattern.
You find the pattern, you find the cause. Then you can address them systemically. For example, if a certain part consistently jams in a specific feeder mechanism only when running product B, you can investigate and maybe re-engineer that specific mechanism or adjust the settings for product B.
And does it work?
We've seen this shown to reduce the number of microstops by up to 20%, sometimes even more. That directly recaptures lost performance that was previously completely invisible and just accepted as part of the process.
20% fewer microstops. That's like finding free production hours hidden in plain sight.
It really is. Making the invisible visible truly pays off.
So making the invisible visible truly pays off. What about quality improvements? How do these technologies help reduce defects on the fly, maybe even prevent them?
For quality, we see significant gains from implementing automated quality control systems integrated with the data platform.
Like cameras or sensors?
Exactly. By implementing smart sensors, high-resolution vision systems, or even AI-powered cameras that perform real-time checks as products are being made, you can catch defects immediately, sometimes even predict and prevent them before they fully form.
How so?
For instance, a system might detect a slight deviation in a component's dimension or color instantly, maybe even a trend towards going out of spec. It could then trigger an alert, automatically adjust a machine parameter, or divert the potentially defective item before it proceeds further down the line, causing more waste.
So it's proactive quality control.
Exactly. This proactive approach significantly reduces the number of defects and rejects, often by 10–15% or more, directly boosting the quality component of OEE. It means less rework, less scrap material, and higher throughput of good sellable products the first time.
And finally, taking all this data, all these insights from availability, performance, and quality, can you use it to optimize the overall flow? It sounds like the system could potentially become a master scheduler almost.
That's a great way to put it. The holistic insights you get from continuous OEE analysis, especially when visualized and simulated through a digital twin, allow for optimizing machine schedules and production flow in ways that were previously impossible.
How did that work?
You can see dynamically how one machine's downtime or slowdown impacts everything downstream, or how adjusting speeds in one part of the line might create unforeseen bottlenecks, or conversely, unlock opportunities further down.
Seeing the ripple effects.
Exactly. This leads to better sequencing of production orders, more efficient batching strategies, better load balancing across available equipment, and significantly reduced idle times waiting for upstream processes. We typically see this resulting in an 8% or higher increase in overall performance just from smarter scheduling.
8% more output just by running things in a better order.
It's about orchestrating your entire production process like a finely tuned symphony, rather than just letting each instrument play whenever it feels like it.
These aren't just theoretical numbers then. These are examples of tangible, measurable benefits that come directly from systematically applying OEE principles and leveraging supporting technologies like DBR77 provides. And those quick wins, like the changeover reductions, must build serious momentum and demonstrate rapid ROI. It really validates the investment, doesn't it?
They absolutely do. Seeing these improvements rapidly, often within weeks or months, not only boosts the bottom line directly, but also builds crucial confidence and enthusiasm within the organization to pursue further, perhaps larger scale, optimizations. It's a powerful demonstration of how data and technology translate directly into operational excellence, making the business case for deeper digitalization very clear and compelling.
We've talked a lot about the technology, the IoT sensors collecting data, the digital twins simulating scenarios, the AI finding patterns. It's all incredibly powerful stuff. But this isn't just about machines and software, is it? It feels like it's fundamentally about the people who operate and manage these systems every day. Without their buy-in and engagement, even the best tech can fall flat.
You've hit on an absolutely crucial point. OEE improvement is decidedly not solely a technological undertaking. It fundamentally relies on human engagement, collaboration, and willingness to adapt.
The human engine, perhaps.
That's a good term for it. Technology provides the data, the visibility, the insights. But it's people who interpret those insights, who implement the changes on the shop floor, who make the adjustments, who troubleshoot the unexpected, and who ultimately drive that culture of continuous improvement. Neglecting the human element is probably one of the most common mistakes that can undermine any digital transformation effort, no matter how sophisticated the tech is.
So how do you get everyone on board and actively involved? What's the secret to making the human engine run efficiently for OEE, especially when it involves introducing new tools, new metrics, new ways of working? That sounds like a challenge.
It can be, but it's achievable. One of the most effective strategies we see working consistently is introducing daily production meetings, or sometimes shift huddles.
Short meetings.
Yes, they should be short, focused stand-up meetings, maybe 10-15 minutes at the start or end of each shift. The team gathers around a board or screen showing the latest OEE indicators and, critically, discusses the identified causes of losses from the previous period.
What's the focus?
It's not about pointing fingers or blame. It's about collective problem solving. Okay, team, availability dipped yesterday because of issue X. What did we learn? What can we try differently today? This fosters transparency, ensures everyone understands the current challenges, and enables immediate problem solving right there at the team level.
So it's about rapid iteration and collective ownership.
Exactly. Here's what happened yesterday, here's the data, here's what we're going to try today to improve it.
And I imagine linking OEE improvements to team goals helps motivate people, making it a shared success rather than just another top-down metric.
Definitely. Team-based motivation is incredibly powerful. By motivating employees through team goals directly linked to OEE improvement, you encourage collective responsibility and shared success.
How might that look?
Well, when everyone knows their individual and team efforts contribute directly to a common measurable goal, like, say, reducing microstops on line 3 by 5% this month, it creates a sense of unity and drives proactive problem solving. If they achieve it, they celebrate as a team. This is far more effective than focusing on individual errors or blame, and it fosters a much more positive environment for change and improvement.
I can see how involving the people closest to the machines, the operators themselves, would be absolutely key. They must see things that management or even the sensors might never catch, those tiny nuances, those workarounds.
Absolutely essential. Operator empowerment is vital, stressing the importance of involving operators who are on the front lines day in and day out in data collection, like accurately classifying stops when needed, and especially in proposing improvements, is non-negotiable.
They're practical insights.
They're practical insights into how machines truly behave in the real world, where the subtle bottlenecks really are, or why certain microstops keep happening are invaluable. They often have the most direct, actionable ideas for improvement because they live with the machines every single day. Their knowledge needs to be actively solicited, genuinely respected, and incorporated into the solutions.
So they feel heard and valued.
Exactly. If they feel heard and valued, they become champions of the process, not obstacles to it.
And for all this to stick, for it to become the new way of working, there needs to be a culture of continuous learning, right? Probably not just a one-time training session on OEE and then you're done.
Precisely. You can't just drop a new system on people. We strongly advocate for continuous learning. This means providing regular, ongoing training, not just on how to use the new tools, but on how to interpret OEE metrics effectively and how to apply continuous improvement methodologies.
Methodologies like Kaizen.
Exactly. Think about proven frameworks like Kaizen, which emphasizes small incremental improvements made every single day by everyone, encouraging people to constantly look for tiny efficiencies. Or Total Productive Maintenance, TPM, which focuses on involving all employees in maximizing equipment effectiveness through things like proactive maintenance, operator self-sufficiency in basic care, and systematic loss elimination.
So it becomes part of the culture.
These methodologies provide the structured approach needed to sustain OEE gains over the long term. They make improvement a daily habit, not just a special project or event.
This all sounds great in principle, but let's be honest, it can represent a high barrier for companies, especially smaller ones, that maybe haven't fully embraced digitalization yet. New software, new metrics, new ways of working, it's a big ask. How does a platform like DBR77, for instance, specifically help with this human engine aspect and make it easier for teams to adopt these technologies and this mindset?
That's a really important question, and it's where DBR77's deliberate human-centric design philosophy truly comes into play. They recognize this challenge early on. They directly address that high entry barrier problem often faced by companies without extensive prior digitalization experience.
By making it simple.
Primarily, yes, by making the platform incredibly intuitive and user-friendly. They worked hard to ensure that the underlying complexity of the technology, the IoT connectivity, the AI algorithms, the sophisticated digital twin models, is largely hidden behind a simple, clean, accessible interface.
So it's not intimidating.
The goal is that users at all levels, from a shop floor operator who just needs to quickly log a reason for a stop using a tablet, to a plant manager analyzing complex dashboards, to a process engineer digging into detailed trends, can quickly understand and leverage the power of the system without needing weeks of specialized technical training or constantly calling IT support.
That accessibility must be key.
It is. And DBR77 further supports this human element with an extensive base of educational materials readily available. This includes their Academia DBR77, which is a structured online learning program, along with numerous detailed case studies showing real-world applications, and regular webinars covering specific features or improvement techniques.
So they provide ongoing support.
Yes, this proactive approach to user education ensures that internal teams can rapidly gain proficiency and confidence in using the platform effectively. It significantly reduces the friction often associated with adopting new technologies and, importantly, eliminates the need for constant reliance on expensive external IT experts or consultants.
Empowering the internal teams.
Exactly. By simplifying access, providing robust educational support, and designing for ease of use, DBR77 ensures that the human element isn't just considered, but is truly empowered to drive the digital transformation and OEE improvement from within the organization.
Okay, so we've got the data flowing in from the IoT sensors. We're using powerful digital twins to simulate possibilities, and we're actively engaging our teams. But all this complex information, all these numbers and trends, it needs to be understood quickly and intuitively by people who need to make decisions.
Yeah.
How do you take these deep insights and make them truly actionable through visualization? How do you make it so anyone can grasp the situation at a glance?
That's absolutely critical because raw data, even perfectly collected real-time data, can just be overwhelming noise if it's not presented effectively. Effective visualization transforms that raw data into actionable intelligence. One key tool for this is the use of virtual control panels.
Like dashboard.
Exactly, like a dynamic real-time dashboard. These typically display current OEE indicators, availability, performance, quality right up front, along with key submetrics that drive them. They provide an immediate, at-a-glance snapshot of operational health.
So you know instantly if things are good or bad.
Right. It allows managers or supervisors to see if a particular line or machine is underperforming right now, not just finding out at the end of the shift or in a report next week. It's kind of like a pilot's cockpit display, showing all the critical flight parameters instantly. You know immediately if you're deviating from your optimal course and need to take action.
So like a live heartbeat monitor for the factory floor. That makes sense. And what about pinpointing where the problems are physically occurring? I imagine a long production line could have multiple machines, and maybe one specific machine is the consistent troublemaker causing delays.
For that specific challenge, we often use downtime mapping. These are visual tools that pinpoint exactly where the most frequent or the longest duration stoppages are occurring across a production line, a work cell, or even an entire facility layout.
How'd that look?
Imagine a floor plan of your factory displayed on a screen. Certain machines or workstations might be highlighted in different colors, maybe shades of red, showing areas with a high frequency or long duration of downtime based on the real-time data.
So the problem areas jump out visually.
Immediately. It draws attention directly to the problem zones and helps prioritize where to focus limited improvement resources, whether it's investigating a specific piece of equipment, addressing a bottleneck in material flow between two stations, or maybe looking at an area with unusually high defect rates. It answers that crucial question: where should I send my maintenance team or my engineers first?
That's a great visual for allocating resources effectively. And there's a well-known principle, the 80-20 rule. that often comes into play when analyzing problems, right? Focusing on the biggest culprits first.
Yes, absolutely. That's where Pareto analysis of losses becomes invaluable. The 80-20 rule, or the Pareto principle, suggests that in many situations, roughly 80% of the problems or losses come from only 20% of the causes.
The vital few.
Exactly, the vital few causes versus the trivial many. Pareto charts visually represent this principle. They typically show the frequency or the impact, like total minutes lost, of different loss causes, ranked in descending order from left to right.
What might that reveal?
For example, you might analyze your downtime data and discover that while you've recorded 20 different reasons for machine stops over the past month, just 3 of them, let's say, material jams in feeder A, worn tooling on station B, and maybe waiting for operator C, actually account for 75% of all your lost production time.
So you focus on those 3 first.
Precisely. This analysis helps identify the few critical problems, that vital 20% that are responsible for the vast majority of your overall OEE losses. It allows for highly focused improvement efforts, ensuring you're tackling the problems that will yield the biggest return on your effort and resources. You're not just tackling problems randomly, you're tackling the right problems first.
So you tackled the biggest offenders first. Makes sense. What other visual tools are commonly used to really help people understand and interpret all this operational data?
Another powerful visualization tool, especially for understanding process flow and conditions, is the use of heat maps of production lines.
Heat maps, like weather maps.
Sort of similar in concept. These are graphical representations that visually identify the most critical or potentially problematic points in a process flow or across a machine. Often they use color gradients, typically from cool blues or greens for good conditions to hot reds or oranges for problematic ones, to show areas of high stress, high temperature, excessive vibration, high cycle time, or general inefficiency.
What would a hot spot indicate?
A hot spot on the map immediately indicates an area needing attention. Maybe it's an overheating motor detected by a temperature sensor, a section of the conveyor line experiencing frequent jams tracked by stop sensors, or perhaps a workstation where production consistently slows down because of material flow issues identified by cycle time data.
So it gives an intuitive feel for the pain points.
Exactly. It provides an intuitive, almost visceral understanding of where your operational pain points are located within the process.
And all these sophisticated visualization tools, the dashboards, the downtime maps, the Pareto charts, the heat maps, they must be powered by some serious analytical horsepower working behind the scenes, right? This sounds like where DVR77's AI capabilities really come into their own. It sounds like their AI acts almost like a virtual consultant, constantly sifting through mountains of data.
That's a perfect description. DVR77's AI systems are essentially the brains behind the visualization and operation. They analyze the vast amounts of real-time data collected via their IoT sensors and incorporate the comprehensive insights derived from the digital twin simulations.
And what does the AI do with that data?
This AI acts much like a virtual lean manufacturing consultant, constantly sifting through the data streams to not just identify current inefficiencies or historical trends, but increasingly to predict potential failures before they happen, and even suggest optimal courses of action to prevent them or mitigate their impact.
So it's not just showing you a problem, it's recommending a solution.
More and more, yes. For instance, it might identify a subtle upward trend in a specific machine's vibration signature that its algorithms recognize as a precursor to bearing failure. It could then automatically generate a recommendation for proactive maintenance during the next scheduled downtime, potentially preventing a costly unplanned breakdown.
That's powerful. Predictive.
Furthermore, this AI utilizes machine learning techniques to generate synthetic data.
Synthetic data, fake data. Why?
It sounds counterintuitive, but it's incredibly useful. Real-world operational data might have gaps, or you might not have enough historical data for every single possible failure scenario, especially for rare but high-impact events like a catastrophic failure on a brand new machine model. Synthetic data, intelligently generated based on known parameters in physics, helps fill these gaps.
How does that help?
It creates a more robust and diverse dataset for training the AI's predictive models. This makes its predictions and recommendations even more accurate, particularly for those rare but potentially very costly events. It helps the AI learn faster and anticipate better.
Okay, that makes sense.
And finally, to make all this truly actionable for busy managers, DBR77's AI automatically generates reports and clear, concise recommendations. It uses advanced language models, like those powering chatbots, combined with statistical analysis.
So it explains things clearly.
Yes, it's like having an expert analyst summarizing thousands of data points and complex trends into easily digestible reports that tell you not just what's wrong, but often why it's wrong and what you should consider doing about it, using natural language that's easy to understand and act upon. This comprehensive suite of analytical tools powering the visualizations drastically facilitates rapid data-driven decision-making for managers, ensuring they can effectively use these tools to drive real, impactful change.
It's one thing to talk about these advanced technologies, IoT, digital twins, AI, sophisticated visualizations in theory, but it's always another thing entirely to see them in action, delivering tangible, real-world results. Do we have a specific example, maybe from our source material, of DBR77 actually transforming OEE for a client? I always love a good success story. It makes it feel more real.
We certainly do, and it's a really compelling case study that perfectly illustrates how all this theory translates directly into measurable impact. Our source details a specific production plant, doesn't name them, but describes the scenario that made the decision to implement the DBR77 platform.
What were their goals?
Their primary goal was twofold. First, they wanted to monitor their OEE much more accurately and reliably, moving beyond their old methods of manual logging and rough estimations. Second, and crucially for them, they wanted to specifically analyze and understand those previously hidden microstops that they suspected were draining their efficiency, but couldn't really quantify or pinpoint the causes of.
So they knew they had issues with those little stops, but couldn't prove it or fix it?
Exactly. They had a hunch, a feeling, but lacked the hard data and the tools to really dig into it effectively.
So they were targeting those death by 1,000 cuts issues head on. How did DBR77 help them pinpoint the specific problems that were unique to their operations? What did the system uncover?
Well, through the intelligent use of DBR77's integrated platform combining the real-time IoT data collection with the analytical power of its digital twin, the plant was able to precisely identify its key OEE loss areas.
What did they find?
The twin's simulations, fed with the real data, and the subsequent analysis highlighted two major culprits that were significantly impacting their overall OEE. First, they discovered that their changeover times between different product runs were excessively long, much longer than their old estimation methods had led them to believe. This was directly hitting their availability score hard.
So the reality was worse than they thought.
Significantly worse. Second, the system revealed a substantial, previously invisible amount of wasted time due to waiting for materials to arrive at specific points on the production line. This delay was hitting both their availability, machine idle, and their performance, slower overall flow.
Wow, issues they couldn't clearly see or quantify before.
Precisely. These are the systemic issues that the plant leadership couldn't clearly isolate or measure accurately before implementing the detailed tracking and analysis provided by DBR77, even though they probably knew generally that they were losing time in those areas.
And what were the measurable results once they identified these issues and presumably took action based on the insights? Did they see a significant improvement in their OEE, and maybe how quickly did that happen?
The results reported were quite impressive and, importantly, remarkably rapid. In just 6 months, which is a very short time frame for seeing payback on this kind of complex operational transformation.
6 months, that's fast.
Very fast. The plant saw its overall OEE jump significantly, reportedly going from an average of 62% to 75%.
62 to 75, that's a massive leap, 13 points.
It's a huge improvement in operational effectiveness. That translates directly into substantially more sellable products coming out the door with the same resources, same machines, same people, same shifts, pure efficiency gain hitting the bottom line.
And did it help with quality, too?
Yes. Simultaneously, demonstrating improvements across the board, the number of product defects recorded decreased by a notable 12%.
12% fewer defects.
Which means less rework needed, less material scrapped, less wasted capacity, and ultimately higher customer satisfaction because of more consistent product quality.
Wow, those are incredibly clear, measurable gains right there.
Mm-hmm.
Did DBR77 help them beyond just those direct OEE numbers, maybe in a broader strategic sense, like planning for the future?
Yes, apparently the benefits extended beyond just optimizing the core OEE metric day to day. The source mentions that DBR77's digital twin capability also allowed this particular plant to simulate and evaluate alternative production line layouts before making any costly physical changes.
Testing layouts virtually first.
Exactly. This virtual optimization, conducted safely within the digital twin before any real-world modifications were made, directly led them to identify and implement a new layout that resulted in a measurable reduction in overall order fulfillment time.
So they got faster at delivering customer orders too.
Right. By seeing how changes in layout would impact material flow, machine utilization, and potential bottlenecks, they could design and implement a more efficient physical space. This demonstrates how platforms like DBR77 provide broader operational improvements, allowing companies to not only optimize their current processes reactively, but also to strategically plan and design for a more efficient, agile, and competitive future operation.
This case study truly illustrates how integrating these advanced technologies, the IoT, the digital twins, the AI analytics as offered by DBR77, translates directly into significant, measurable improvements in operational effectiveness and ultimately the financial results. It really reinforces DBR77's claim that it improves client OEE.
It certainly does.
And it also clearly addresses that high ROI requirement challenge that many potential industrial clients understandably have. By providing a clear example of rapid, significant returns on investment, seeing a 13-point OEE jump and 12% defect reduction in just 6 months, it makes the business case much stronger. It's not just about a promise of future benefits. It's about proven, near-term impact.
Precisely. It's not just about providing the sophisticated tools, it's about enabling tangible bottom-line impact and demonstrating a potentially faster payback period, which makes the investment incredibly attractive, especially in competitive markets.
That success story is incredibly powerful and really shows what's possible when these tools are applied effectively. But like any complex analytical tool or methodology, there must be pitfalls in OEE analysis. What are some of the most common mistakes companies make, even when they're genuinely trying to improve their operations and use these metrics? Where do people often go wrong?
Oh, it's true. Even with the best intentions and access to advanced tools, companies can definitely stumble when implementing and interpreting OEE. One very common mistake we see is zooming out too much or analyzing at too high a level.
What do you mean by that?
Many organizations initially analyze OED only at the level of the entire plant, or maybe a very broad department, rather than drilling down to individual machines or specific production lines or work cells.
Looking at the average for the whole factory.
Exactly. And this broad aggregate view can easily obscure specific localized problem areas. For instance, a plant-wide OEE might look somewhat acceptable on average, maybe hovering around 70%, which doesn't raise major alarms.
Dude, okay.
But hidden within that average, individual machines or critical lines could be performing terribly, maybe down at 40% OEE, while others are running exceptionally well at 90%, dragging the overall average up without the specific poor performers being easily identifiable or prioritized.
So the average hides the variation.
Precisely. You need granular insights down to the asset or line level to effectively target improvement efforts. Otherwise, you're looking at the forest when you really need to fix a specific struggling tree.
And I imagine ignoring those micro-stops is still a big one, even with all the talk about them. The temptation to overlook those small problems must be strong.
Absolutely. It's worth reemphasizing that death by 1,000 cuts trap. Ignoring the death by 1,000 cuts, consistently overlooking or failing to accurately measure microstalks remains a critical and surprisingly common error.
Why is it so common if it's so impactful?
Because these stoppages are so short, they're often not logged manually, sometimes not even consciously noticed or remembered by operators who quickly fix them. But as we've discussed, when aggregated, they create substantial hidden losses in performance. Failure to track and address them systemically means leaving significant efficiency gains, potentially hours per day, completely on the table.
So you have to measure the small stuff too.
We often find that once these microstops are accurately measured using automated systems, they can account for 10%, 20%, sometimes even more of all lost production time, easily outweighing the impact of less frequent but more dramatic major breakdowns over a year.
So you need granularity, and you need to look at the small things. What about when you do identify an issue, maybe a longer stoppage, but you mislabel it or don't get to the actual core cause?
That's another major pitfall. Vague or incorrect problem classification. This means wrongly, or just too generally, classifying the root causes of losses. The classic example is generically attributing almost everything to equipment malfunction or maybe operator error without conducting a deeper analysis to find the specific root cause.
Just picking the easiest category.
Right. If you simply classify a stop as a generic breakdown, you don't know if it's a specific mechanical issue, an electrical fault, a sensor problem that needs recalibrating, a material flow issue upstream, or maybe even a flaw in the product design causing jams. This lack of specificity prevents effective, targeted corrective action because you're not addressing the true underlying issue.
So the problem keeps coming back.
Exactly. You're just putting a Band-Aid on a symptom and the problem will likely recur. A proper classification would be much more specific, like hydraulic pump failure on main press axis. Suspected root cause is clogged intake filter. That tells you exactly what to investigate and fix.
And finally, maybe the most frustrating one for anyone genuinely trying to drive improvement. Gathering all this data, doing the analysis, identifying the problems, generating reports, and then nothing actually happens. The dreaded analysis paralysis.
Indeed. Perhaps the biggest mistake of all is analysis paralysis. This is the phenomenon of collecting vast amounts of data, performing sophisticated analysis, creating detailed charts and reports, but then failing to translate those insights into real, concrete, corrective actions on the shop floor or in the process design.
All talk, no action.
Pretty much. Data collection and analysis are only valuable if they lead directly to tangible changes in processes, equipment maintenance, operator training, scheduling, or material handling. If you're just monitoring and observing, generating beautiful reports that sit on a shelf, but not actually acting on the insights gained, you're essentially investing time, resources, and potentially significant capital into a purely academic exercise that yields no real operational improvements.
So the data must inform decisions and drive action.
Absolutely. Otherwise, it's just expensive information gathering, not performance improvement.
So how does a platform like DBR77 aim to mitigate these common mistakes for its users? And maybe also address some of the broader challenges companies face when adopting these kinds of new digital transformation platforms, things like the perceived complexity of integration or how they compete against much larger established players in the industrial automation space?
That's a great question, because adoption hurdles are real. DBR77 seems to have systematically addressed these challenges through both its platform design and its overall business strategy, regarding the complexity of integration, which is often a major barrier.
Yeah, ripping out old systems sounds scary.
Right. DBR77 operates primarily in a browser-based environment. This significantly simplifies deployment for the client because there's generally no need for them to overhaul or drastically modify their existing core IT infrastructure, like their ERP or MES systems.
So it works alongside existing systems.
Yes, its well-designed API, application programming interface, facilitates seamless integration. It can pull necessary data from and push relevant data back to existing ERP, MES, or WMS, warehouse management systems. And crucially, DBR77 provides dedicated IT support during implementation and beyond, which helps minimize the costs and risks for the client, directly tackling that complexity of deployment problem that often delays or even derails digital transformation projects.
Okay, that helps with implementation. What about competition from large players? I mean, you have giants like Siemens, ABB, Rockwell Automation in this space. How does a company like DBR77 compete?
DBR77 has taken a smart, strategic approach here. They initially focused heavily on serving small and medium enterprises, SMEs, a huge segment of the manufacturing market that was often overlooked or felt underserved by the larger providers whose solutions were sometimes seen as too complex or expensive.
Targeting a different niche initially.
Right. They offer a more accessible entry point, often through a flexible subscription model rather than a massive upfront capital expenditure. They emphasize achieving rapid ROI, which makes it a much more appealing choice for businesses that are sensitive to initial investment costs. Interestingly, this successful approach with SMEs has also started attracting larger corporations.
Really? Why?
Because those larger companies are sometimes looking for greater flexibility, faster deployment, or lower initial costs for specific projects or divisions compared to traditional, monolithic, large-scale deployments that can easily run into hundreds of thousands or even millions of euros or dollars. DBR77 offers a modular, scalable solution that can grow with the company's needs.
So it's about offering accessibility and flexibility. That must also help with the challenge of building a strong partner network needed for implementation and support, especially internationally.
Exactly. Building a robust ecosystem is key. DBR77 addresses that challenge head-on by establishing and nurturing a vast online marketplace. This connects manufacturing companies looking for solutions with, reportedly, over 800 technology providers like sensor makers or automation specialists, and over 600 system integrators who can help implement the platform.
A one-stop shop.
It creates a powerful one-stop shop ecosystem. This significantly speeds up implementation for clients as they can easily find certified partners, and it lowers costs through competition and specialization. It also provides a ready network for partners to find new business opportunities. It's designed as a win-win-win, building a supportive community around the platform.
Okay, that makes sense for scaling. What about data security and compliance? That must be a huge concern for any company putting sensitive operational data into a cloud platform.
Paramount, absolutely paramount. DBR77 emphasizes that it operates under the stringent ISO 27001 standards, which is a globally recognized certification for information security management systems. All client data is stored securely on reputable cloud servers, they mention, using AWS servers located in Frankfurt, Germany, which helps ensure compliance with strict data privacy regulations like GDPR in Europe.
And contracts.
And because it's a purely B2B platform dealing with sensitive industrial data, all users, clients, and partners are required to sign robust non-disclosure agreements, NDAs, ensuring maximum legal protection for confidential operational data. Data integrity, security, and privacy are clearly stated as top priorities.
And for companies looking to expand globally, or those that already have international operations, what about the challenge of difficult international expansion for a platform provider? Adapting to local needs and regulations.
DBR77's strategy here relies heavily on collaboration. They actively partner with local system integrators and distributors in different countries and regions, many of whom already have international operations and deep local market knowledge.
Leveraging local expertise.
Exactly. This approach leverages existing local expertise, languages, business practices, and relationships. It significantly simplifies the process of adapting the platform and its implementation to meet specific local requirements and regulations, accelerating DBR77's expansion into new key markets like Germany, the US, or parts of Asia. They don't try to do everything themselves from headquarters, but build strong local partnerships.
And finally, in such a rapidly evolving tech landscape, how do they address the constant necessity for continuous AI and digital twin development? Technology changes so fast.
They have to stay ahead. DBR77 emphasizes continuous investment in research and development. They leverage the vast amounts of anonymized, real-world operational data and the synthetic data they generate collected across their platform to constantly train and refine their AI algorithms. This ensures their predictive models for things like failure analysis or performance optimization are always improving based on the latest insights.
Learning from the data.
Learning from the collective data pool. They also maintain direct collaboration with technology providers like machine builders or sensor manufacturers to ensure they have updated information on the latest equipment capabilities and potential failure modes. And they highlight their ongoing development in areas like spatial analysis within the digital twin, keeping them at the forefront of applying AI innovation specifically for industrial operations. It's a clear commitment to long-term technological leadership, ensuring the platform remains cutting edge and continues to deliver increasing value to its users over time. #OutRoGurn.
Well, we've certainly covered a remarkable amount of ground today in this deep dive into OEE and the technologies shaping modern operations. We started with a comprehensive exploration of overall equipment effectiveness, really understanding its three core components: availability, performance, and quality, and how they multiply together to define the true health of, well, almost any operational process.
We did. And then we moved into unpacking the subtle, often invisible ways inefficiencies creep in, going beyond the obvious breakdowns to look at things like long changeovers, slow cycles, quality losses, and especially that insidious death by 1,000 cuts caused by those frequent tiny microstops.
Yeah, the microstops really stuck with me. Then we explored precisely how cutting-edge technologies like the Internet of Things for data collection, sophisticated digital twins for simulation and prediction, and powerful AI for analysis, as brilliantly demonstrated by platforms like DBR77, can fundamentally transform operational effectiveness.
Absolutely. We've seen how precise real-time data collection, combined with advanced simulation capabilities in a virtual environment, and critically truly engaged and empowered teams, can unearth those previously hidden losses and drive really significant, measurable improvements. That case study was fantastic. Seeing a plant jump from 62% to 75% OEE in just 6 months is proof of the potential.
It really is. It's clear that the future of industry, and maybe productivity in general, is deeply intertwined with these digital solutions. They're enabling levels of efficiency, prediction, and insight that, frankly, we could only dream of just a decade or so ago.
The pace of change is incredible.
And that brings us to our final provocative thought for you, our listeners. As technology continues to evolve at this astonishing pace, the distinction between the physical and digital worlds, particularly in industry, is increasingly blurring. DBR77's long-term vision, as mentioned in our sources, includes developing a full Industry 5.0 platform.
Industry 5.0, what's the focus there?
The aim is to seamlessly integrate intelligent automation, not just with machines, but also with personalized employee support and collaboration. This future envisions managing not just robots and machines optimally, but managing robots and humans in an integrated, harmonious, and mutually supportive way. The goal is to further boost overall operational efficiency and resilience to levels we haven't reached yet.
So leveraging the best of both humans and machines together.
Exactly. So the provocative thought is, what does this potential future of deeply integrated human-machine optimization mean for your own understanding of efficiency, collaboration, or even job design? How might you leverage these core principles, maximizing availability, optimizing performance, ensuring quality, and fostering collaboration even on a smaller scale? Perhaps in managing your team, optimizing a complex project, or simply fine-tuning your own daily workflow. Could understanding and tackling your personal micro-stops lead to your own significant OEE jump?
It's a fascinating question to ponder. Where can these principles take us next?
If this deep dive has piqued your curiosity about digital transformation in industry, or specifically how these powerful technologies like OEE tracking, IoT, and digital twins could impact your own operations, you have a few ways to explore DBR77 further, based on our sources.
That's right. You can apparently register directly on their platform via their website to get started and explore its features yourself. Or, if you prefer a more guided approach, you can reach out to their sales team to request access to a test version of the platform and dive deeper into its capabilities.
And if you want to see the technology in action and discuss how it could be specifically applied to your unique situation, your challenges, your goals.
Then you can book a personalized demo meeting directly with their team. The information for all these options should be readily available on their website, helping you take the next step towards achieving operational excellence in your own context.
Fantastic. Thank you for joining us on this deep dive into OEE and the future of operational efficiency. We hope it's given you some new insights and perhaps some practical tools to think about effectiveness in a whole new way.
Thanks for listening.
Until next time.